So this is ibuprofen. So let's say this is a typical workflow. So I've got my structure and I'm interested, okay, well, what does my particle look like? So I fire up the morphology. I say, okay, well, there's some interesting facets here. Firstly, I see that the sort of 100 facet is the biggest facet that's on this crystal. And then I notice that this 002 is a relatively small facet, not the smallest, not the largest, just somewhere in the middle. So I'm gonna explore those two different surfaces. So what you can do is you go to surface analysis, and this dialog pops up, and you can input your HKL values. So I'm going to go for 002 to start with. I'm going to leave the offset as 0, and I'm going to hit calculate surface. And as you can see, very quickly, we get a resulting surface. Now, the results section has been populated with the chemical descriptors here as the density info and the topological descriptors. Now, when I say topology, what I'm referring to is this off-white property, this sort of shape, and its roughness is all described by these descriptors. So the rugosity, the RMSD, the skewness, and the kurtosis. My favorite is the rugosity, and the reason for that is that it just perfectly captures the roughness in one value. The higher the rugosity, the more rough your surface is. Now, of course, this off-white is really easy to look at, but it's not the most informative if you're interested in roughness, for example. So what you can do is you can change that surface coloring to topology. Now, instantly we get a visual response as to where are the highest points of this surface and where are the lowest. Now, this is all relative to the mean plane where we've defined the HKL. So the further down you go, the colors will turn purple. You can sort of see it turn a little bit purple here. And the higher up you go, it'll go red. You can see, if you just look closely, you can see the top of that peak is a dark orange, we'll say. So this will very quickly allow you to check the surface roughness. Now let's say I check for the 100 surface, which was our really big facet. So if I hit calculate, leave the topology on, instantly I can tell without even looking at the numbers, this is a much smoother surface by the fact that this surface is mostly green. There is a little bit of blue in there to sort of signify the valleys, but I'm pretty confident that the 002 is a much rougher surface than the 100. Now, the other display options that we can change are the atom properties. So this allows us to overlay all our chemical descriptors onto the surface. So not only do you know what density you have, but you know where it is. And the where it is really crucial when it comes to surface properties. So I'll switch on hydrogen bond acceptors and donors. And if we zoom in and turn on hydrogen bonds, you can see that it's correctly mapped. So here we have a carboxylic acid sort of in a dimer. So you've got donors and acceptor group. Yeah, that's right. And then if we look up at the top here on the surface, you see we've got hydroxy group here with the hydrogen sticking out of the surface. That's a donor. And then on the other side, we have the carboxylic group that sort of sat as an acceptor on the surface as well. Also right. So very quickly, you can get visual representation. Okay, I have a donor sitting on the surface right at the peak, ready to be donated. And I've got a dimer in a valley. So you can quickly make an assessment as to what your surface chemistry might be able to do. Now, all things, so in terms of hydrogen bonding, it's very important to sort of understand when a hydrogen bond is available for donation. So we have this extra category called an unsatisfied hydrogen bond donor. So if I toggle that on, you'll notice this will go a light blue color, whereas this one down here does not. And the reason for that is that the hydrogen in this hydrogen bond is already being used in part of the surface, whereas the hydrogen up here for this hydroxy group is not being used. So it is available for donation. And that is very important to understand. And then, of course, we can turn on the aromatic bonds, so we can see where those are on the surface. So if we look at our ring, we can see that that lines up with the surface, which is great. And then finally, for the atom properties, you can visualize the charge. So by default, this will use the Gasteiger charge to show you the sort of partial charge of your atoms. You can add your own partial charges if you wish. There's a little tip for that in the handout. But in essence, that's the atomic properties sort of options that you can visualize. Now, with all that being said, let's say that you've got your surface, you're really happy, and you want to publish it. You know, you're like, it's a little bit too small. People might not think it's a surface. What you can do is you can go to the Advanced Options tab, and you can make it bigger. So I'm going to set a 2x2, hit Calculate. It will take a little bit longer because it is making a bigger surface. So there's more triangles to render. What you'll notice straight away is that we have a 2x2 representation. What you can also do is, say you want to do an MD calculation and you want to generate a surface. By default, we display an extended view, which means that every molecule that has an atom underneath the topology will be displayed on screen. But what you can do is you can show the periodic view, which basically shows you all the unique representations of the atoms that are within the bounding box that determines the surface. Now, if you want to see what that bounding box looks like, you can click the Preview Slab button, and that will give you the overlay of the bounding box that defines your surface. And what you'll notice is that it gives you the U and V vectors, which is the two vectors that create the repeat unit area, and then the W, which is the thickness. And you can vary the W to make it thicker or thinner. As Andy mentioned, defaults are good. Use at your own risk on that one. If you make a really thick slab, it will take a bit longer. But if I increase the values here, it will automatically increase the periodic boundary before calculating the topology. So you can get a rough idea of what you might be getting. The other useful thing about the preview slab functionality, say that you want to, say you've got your structure, you don't know what facet you want to look at, so you want to sort of explore the different orientations. You can put a preview slab on, as in tick the box, and then you can just sort of go to 3 different HKLs and just explore what kind of surface chemistry you might see. And you see this will, on the fly, update as you sort of iterate through the different facets. And that, in essence, is surface analysis. Now, where this gets really powerful is when you start to introduce the data from the CSD with the full interaction maps. So there's a button here that you press, and that opens up the dialog. And by default, the uncharged NH nitrogen, the carbonyl oxygen, and the aromatic CH carbon are selected. So what we can then do is, for these given probes, we can calculate what the different potential interactions are with our surface. So if I hit Calculate Surface, what you'll notice on my very lightweight computer is it'll go away. I just heard the fan spin up. It'll go away and calculate the positions and the probabilities of finding these probes on this surface. And what you notice is that we have a very interesting agreement between the surface chemistry and the potential interactions. So just to clarify, the red maps are acceptor probes, the blue maps are donor probes. So what we would expect is for the acceptor probe to be near the donor atom on the surface. And that's exactly what we see. So if I put in the atom properties and put in hydrogen bond donors, you see that this red map is exactly where our hydrogen is positioned for donating, which is really good because that means that we are sort of marrying up together the surface chemistry and the potential interactions with things coming onto the surface. And what you'll notice is that for the dimer down here, where we still have hydrogen bond donating groups, there were no potential interactions from the acceptor groups from the full interaction maps. Now, this data is really useful for understanding sort of steric hindrance and where you might find chemistries that could potentially fit into your surface. What it also gives us, it gives us a value. So it gives us a metric to be able to compare against between different facets, for example. So here are the maps So these are the three different maps that we just ran on the three probes. So we have the uncharged nitrogen, the carbonyl oxygen, and the aromatic CH. And what you see for the levels column is it gives you a value between 0, or between the minimum and the maximum for these points. Now, what this value describes is the likelihood above random of finding a probe of that selected types of the uncharged nitrogen, for example, in that position with that functional group. So what we can tell here is that, okay, carbonyl oxygen, pretty high probability of finding it in these positions. So we're very confident with that. Now what you can do is, say I calculate the water oxygen probe for the surface. And so first thing you'll notice is the water tends to go in quite a lot of places. But when we look at the values, it goes from 0 to 139. So if we restrict the view to only those above 20, so this is a probability above random, sort of 20 times above random, we can see that this region here is most likely to have an interaction with the water oxygen probe. And the value for that region, the maximum is 139, right? Now, if we go back to our previous facet, the really large one from the morphology, that's the 100, and we do the same calculation. So first thing you have to do is you have to calculate the new surface. So you notice it's the same one, so it's sort of like this really smooth surface. And we use the same probe, so we calculate the water oxygen again. Now, what you notice is that, well, hold on, this is a much bigger phase, a lot less chemistry as well. So if we look at the descriptors, we have 0, 0 for the donors and acceptors, but there's water everywhere. Right, yes, there is potential for water oxygen to interact with the surface. However, when you look at the values for the probabilities, it's much, much lower. So previously we were seeing 139 as a sort of maximum probability value for the other facet. Whereas for this one, we're looking at 25. And with that, you can essentially assess that your 002 is most likely to have water bound to it than your 100. So all of a sudden, you have some information about your particle that you didn't 10 minutes ago. And it was very quick and easy to calculate and fairly trivial to interpret as well. And that, in essence, is the full interaction map on the surface. It allows you to combine the surface chemistry of your facet and all the interaction data from the CSD to see from the functional group that are exposed what's available, like what can actually be interacted with based on steric hindrance.